All right, let's continue our discussion on what we mean by the derivative at a particular point. So this notation here, this limit definition of derivative, we'd read this as the limit as h approaches 0 of f of a plus h minus f of a all over h. We're going to break this down. H, what does that mean first of all? So h is the distance between the point, the x value rather, that we're interested in. So in this case, h was 1, and whatever point we're using to approximate. Really, I called this delta x in the table. I really should have called this h. That probably would have been a better terminology. H is the distance between the points, basically. So the idea is as that distance goes to 0, that means the limit as h approaches 0 of the function evaluated at a plus h. So now we're just going to use h. So instead of using a point and just doing this over and over again like we were doing in that example, we're just going to use h, and we're going to use some algebra to simplify this and find the limit. This seems complicated at first, but once you get the hang of it, it's not so bad. It really becomes just a lot of algebra. This is called the difference quotient for the function of f at a. Let's do an example here. Find the slope of the tangent line to the graph of the function f of x at the point 2, 1. So note that a is the x value that we're interested in working with, so in this case it's going to be 2. So according to this definition, my setup is going to look like this. I want the limit as h approaches 0 of f of 2 plus h, so I'm just going to leave it as a generic h, minus f of 2 all over h. Now, what do these things mean? F of 2 plus h means I'm going to take the function, and wherever there is an x, I'm going to replace it with 2 plus h. So kind of off to the side, if you want to write this out, f of 2 plus h is going to be equivalent to what for this example? F of 2 plus h is going to be 2 times 2 plus h minus 3, because that was the function. All right, let me go back and look. Let me clean this up a little bit so you can see what I'm talking about. Wherever there is an x in that original function, I'm going to replace it with 2 plus h. That's what this notation means. So this expression becomes the limit as h approaches 0 of f of 2 plus h, which is that expression I just wrote out, 2 times 2 plus h minus 3. And then we're going to minus f of 2. Well, what is f of 2? That just means you plug 2 in for x. So f of 2, if I want to come off to the side and work that out, 2 times 2 minus 3 would give me a value of 1. So we're going to minus 1 all over h. And now you're going to do some algebra and simplify this expression. So this becomes the limit as h approaches 0 of, I'm going to distribute the 2, so that gives me 4 plus 2h minus, notice that this negative 3 and this negative 1 can be combined to give me negative 4 all over h. And I'm going to clear some space here just so we don't get confused. That's what we're working with now. Look at what divides out or cancels out in your expression. Notice that the 4's cancel out, and I'm left with the limit as h approaches 0 of 2h over h. Notice that both of those contain an h, so I can cancel that out, and I'm just left now with the limit as h approaches 0 of just the function 2. That's a constant function, so the limit will just be the number itself, which is 2. And that's it. So the slope of the tangent line to the graph of this original function at the point in question is 2, and that's all there is to it. This should make sense because this is, notice, a linear function. The slope of this line would have been 2, and so any point I plugged in, I still would have gotten 2 for this particular function. But more complicated functions aren't going to be quite so straightforward, and we'll do plenty of practice with this in class. So if it's a little fuzzy, just hang in there and we will look it over. A couple of final thoughts here. Notations for derivatives. So derivatives have several notations. Historically, there were some different mathematicians, including Isaac Newton that we're looking at the same topics around the same time, and we're using different notations. And so we have different notations that we use interchangeably. This first one is called f prime of x, is how we would say that. We could also say y prime, so that little apostrophe means prime. dy dx is another type of notation. That means the derivative of y with respect to x. Note that dx does not mean multiplication, so be careful with your thinking on that. dy does not mean d times y, so be careful with your thinking on that. We would read this as the derivative of y with respect to x. It does not mean division, and it does not mean division when we write it this way. df dx, that's another way we might do this. Derivative of f, if that's the name of the function, with respect to x. And occasionally you might see this last notation. Not so common though. The ones that are most common, I would say, are the prime notations and dy dx. So the derivative, remember, is the slope of the function at any given location. It's the slope of the function at that location, really the slope of the tangent line at that location. So if this is the original function, what would the graph of the derivative of this function look like? Well, we can sketch this because these are straight lines. So between 0 and 1, look at that portion of the graph and tell me what the slope of that line is. So we can get the slope of that line by just doing literally rise over run. So notice we go up 2 and over 1. So the slope of that line is 1/2. So on our derivative graph between 0 and 1, we would just do a constant value of 1/2. And try to get that as straight as you can, maybe a little better than I did. And I'm going to leave those open for now on the ends. Now between 1 and 4, I have a slope. If you do rise over run, it looks to me I go up 1 and I run 3. So my slope there would be about 1/3. This is a little messy, but hopefully you see what's going on. I've just got a horizontal line, 1/3. So these are my slopes, don't forget. And then in between, I have a slope of 0. It's a horizontal line segment in the original function until I get to 6. So my slope there would just be at 0. And then now from 6 to 9, I have a negative slope because the line's going down. So I'm going to do rise over run. I go down 3, and it looks like I'm going to go over 3. So my slope down there is -1. And so the graph below, as messy as it is, that's my derivative function. And all this does is model what the slopes are, show you what the slopes are at each of those given segments. Last little section, a couple of things about where derivatives don't exist. Basically, derivatives don't exist when you have corners and cusps. So if you have some kind of a corner in the graph or a cusp, the derivative does not exist. So at x equals 0 in both of these pictures. If there is a vertical tangent in this picture, you would have a vertical tangent. The derivative would not exist, and that would be because the slope would be undefined, just like normal when you have a vertical line. Or if you have a discontinuity, of course the vertical, or the derivative rather, would not exist there. So at x equals 0, here we have a discontinuity. In this last graph, just for good measure here, notice that we had corners where there were changes. And so in those spots, I left the derivative as open circles because the derivative would not have existed at those corners. A function is said to be differentiable if it has a derivative, basically, everywhere in its domain. It must be continuous. So that's the first thing. It has to be continuous. As I just mentioned here, you can't have a discontinuity. And it has to be smooth. It can't have a corner or, like I said up here, a corner or a cusp. If there's any of those hard edges, then it's not differentiable. And functions on closed intervals can have derivatives that are called one-sided derivatives at their endpoints. And we'll get more into this in class, but this is just hopefully to give you a little bit of introduction, and we'll do some practice with this tomorrow.